We'll begin our true venture into metabolism with our first pathway converting glucose into pyruvate called glycolysis. So where does glycolysis take place? Well, the easy answer to that question is in every cell. All cells do glycolysis, but more specifically, it takes place in the cytoplasm. So the bulk of the cells where this occurs. It's a series of 10 enzymes that work collaboratively to convert glucose into a pair of pyruvates, and we're going to get several products out of this, not just ATP. Okay, so a link to a video here I'd like you to watch, and I like this video because when they show the molecules on the screen, the molecules don't disappear and come back as a changed molecule. The reaction doesn't take place off screen. What I like about this video is it shows the bonds being stretched and broken and the new bonds being formed. They don't cut away. Okay, so in between each of the stages, the molecule that's going to be on the screen stays on the screen. Okay, so what I'd like to do is for you to practice drawing these molecules. So start with glucose, pause the video as you go through this 7-minute and 7-second video with her, and know the structures from glucose, adding the first phosphate, putting on the second phosphate, the conversions from ring and straight chain you need to know through there, splitting it into 2 molecules, and then the oxidation step, the only one. We add a second phosphate, we take it right back off. We move an alcohol group or move a phosphate around and then remove the phosphate after we move the double bond to make an alkene. So all these little steps you need to know, we're going to go through, but go through this small video that's linked and she'll walk you through it. You may want to turn the sound off after the first few times and just watch the structures as you go through. Okay, this graphic on the side of this slide here, on the first slide here, is about 75% of what you need to know for this topic, for this course. Okay, so if you know the structures, one way to learn this is memorize those structures, go through it step by step, and then the names follow from the structure. You can tell it's got 2 phosphates. You can tell it's glucose. You know it's fructose, and so forth. You've learned all your sugars already. Another way to learn this is learn the names from step to step. Glucose to glucose 6-phosphate to fructose 6-phosphate, and so forth. And then once you've learned the names in order, you can go back and draw them, however way you'd like to do it. A third way to do it is to learn all 10 enzymes, and the names of the enzymes tell you what's going on for most of them. Hexokinase is fairly obvious. It's going to put a phosphate on a 6-carbon sugar. Well, there's only one place that happens in here, putting it on a sugar that doesn't already have a phosphate. That's step 1. The other one, in step 3 there, is phosphofructokinase. Yes, it's still a kinase. It's going to receive a phosphate, and it's putting it on a fructose, but it's not called fructokinase. It's called phosphofructokinase. And that means it's putting on a phosphate on a fructose that's already phosphorylated. So it's getting a second one. So the names make sense. There's one in here that will not make sense at first. It's the very last one, pyruvate kinase. And we'll explain how that name came about and why we call it that. And so I want to walk you through this pathway one step at a time. And if you want to pause this and watch that other video, that would be great so you know what I'm talking about. But let's start at the top here with glucose. Okay, so look at the structure at the very top right, glucose. What's happening in the first step is we're going to phosphorylate it. Okay, now if you look at glucose's structure, also drawn on the left on the same slide, there are some potential places to put that phosphate. Okay, ATP is going to be our donor of the phosphate, the enzyme hexokinase, and the target of the phosphate is going to be this glucose molecule. Well, where could we put it? Well, we need an oxygen to put the phosphate on, an OH preferably. Well, glucose has 5 available, right? The OH that was on carbon number 5 in its straight chain form is not available because it's in the ring structure at the moment, right? It's occupied in that new bond for the hemiacetal. So instead we have 5 other OHs available. Of the 5 that are available on carbons 1, 2, 3, 4, and 6, which one is the most accessible? Which one do you think? 1, 2, 3, 4, or 6? And why?
Is it 6 because it limits the 1,3 diaxial interactions?
Almost, yes. it's another way of saying that. It's number 6, you're correct. It's the one that is not directly on the ring. Right? The OH is the farthest from the carbons of the ring. In fact, it's not on a carbon of the ring. So it's the most accessible because it's the easiest to get to, right? The others are next to this ring structure. It's not a flat ring, it adopts a chair conformation, but that number 6 is sticking off the ring, right? It's also in an axial arrangement, so it's easy to get to. So that's what the enzyme is going to do. It's going to phosphorylate number 6, right? And that's also shown on the right in the second picture. You see phosphate is now on number 6's carbon. Okay, what happens next is the glucose 6-phosphate opens up into a straight chain form. Right, we no longer have the hemiacetal. It's listed top to bottom, 1 through 6, and there's a phosphate on number 6 at the bottom. And we do a very simple conversion, a very simple isomer formation, right? We're going to convert the glucose into a fructose. We've seen this already. The 6 at the bottom, the phosphate on number 6 doesn't change. It's not involved, but the enzyme does recognize that it's there. So it makes sure it does this to a glucose 6-phosphate and not just the plain old glucose. So it detects that it's there, but it doesn't get involved in the chemistry. So we convert the other end of the molecule, carbons 1 and 2. We move the carbonyl from 1 to 2, making it a ketone. And now we fold it back up into its ring form again, right? Because it's more stable in the ring structure. So now we have fructose 6-phosphate in its ring form, right? So that's also shown on the right in the third picture. The phosphate is still on number 6. It hasn't moved, right? But carbon number 1 is now not in the ring because we have a ketone. Okay, so the second phosphorylating enzyme, or step 3 here, our phosphofructokinase, is going to come along and phosphorylate this molecule. And just like in step 1, which OH is the most accessible?
Carbon 1.
It's carbon 1 now because it's also not in the ring. Well, number 6 is also not in the ring, but it's already got a phosphate on it. It's unlikely to get a second. So we're going to put it on carbon number 1. That makes logical sense. So now we have this fructose 1,6-bisphosphate, and I have a 5-membered ring, 2 carbons not on the ring, 6 carbons total, and 2 phosphates on carbons 1 and 6. And at this point, we're not going to add any more phosphates to this structure, and we've invested some energy. This is called the investment phase. Right? So in steps 1 and step 3, I've consumed an ATP molecule. In fact, I've used it as a donor of high energy phosphates, and I've attached them to this sugar at this point. So if you think of it, if I were to stop here after step 3, I'm essentially not getting anything out of this. I'm in debt for 2 high energy phosphates. So by the time I finish, I better gain back at least 2 high energy phosphates, or this wasn't worth doing. Right? We'll see, we'll get back a total of 4. But so far we haven't gained anything. I'm only invested some energy in the form of phosphates. So in the next part, we're simply going to have this fructose 1,6-bisphosphate open back up into the straight chain one more time. There'll be no more rings after this. Right? So it opens into its straight chain. And if you looked at the fructose molecule on a straight chain, there's a carbonyl on number 2. Carbons 1 and 6 on each end have a phosphate. And what this molecule is going to do is get a divorce from itself. It's going to be split into 2 isomers of each other, even split. Each molecule is going to have 3 carbons. Each is going to get a phosphate, has the same number of oxygens in each and the same number of hydrogens in each. So everything's going to be split equitably. And when you do that, you're going to get a 3-carbon sugar with a phosphate, that's an aldehyde, and you're going to get a 3-carbon sugar with a phosphate, that's a ketone. And that's our 2 products of step 4, our glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. And we'll look at that reaction momentarily. Okay? But these are isomers of each other. So I could convert one into the other. So I could have 2 copies of dihydroxyacetone phosphate, or I could get 2 copies of glyceraldehyde 3-phosphate. And this will go back and forth all the time. It's an easy reversible reaction. It's probably considered the perfect enzyme because of how readily it does this reaction. So now I have essentially a glyceraldehyde 3-phosphate, but 2 moles of it at this point. So step 5 is just interconversion of the 2. But at this point in the process, I effectively have 2 moles of glyceraldehyde 3-phosphate for every mole of glucose that entered. Right? And what we'll do is we'll take the glyceraldehyde 3-phosphate and continue the reactions in stage 3 here. But remember, I'm doing this for a pair of these molecules. I'm not going to draw it twice, but you notice on the left it says 2x or times 2. It's because I'm doing this for 2 molecules. I'm not going to repeat these steps twice. I'm just going to do it for 2 separate molecules. I'm only showing one of them in the picture. Okay? So every step here is multiplied. It's done for 2 different molecules. Okay, so in the third stage here, we're gonna take that glyceraldehyde 3-phosphate and do 2 things at once to it in the next step. We're gonna oxidize it. So the one part of it that's readily oxidized is the aldehyde. You know, aldehydes are reactive. So we're gonna oxidize the aldehyde. When you oxidize aldehydes, you get carboxylic acids. And at the same time, we're gonna put a phosphate on that carboxylic acid. All right, so now we have a phosphoester bond. Right, so we're going to put a phosphate on, same one, carbon number 1. And those 2 reactions, they're really one reaction, it's coupled together. We talked about coupling reactions last time. Okay? So those 2 things happen by the same enzyme, but they happen together. We oxidize it and put a phosphate on. One's favorable, one's not so favorable, but overall the delta G is still rather favorable, okay? Rather than being totally not going to happen. And then after that, we're going to let that phosphate come right back off. And this was one of our 3 molecules, my 1,3-bisphosphoglycerate, one of the 3 molecules that had more energy than ATP. So I could lose its phosphate and give it to ADP to make an ATP in step 7. And then I'm left with 3-phosphoglycerate, the very thing I would have generated if I just oxidized the product from step 5 up there. But I got something out of it because of the way I can put a phosphate on and oxidize it and get energy out of there. So I have a 3-phosphoglycerate. It's a rather stable molecule. In fact, it's very stable. I'd like to make it less stable, to tease some more energy out of it. So what I'm going to do is move the phosphate that's on number 3, clearly by the name, and move it up to number 2, right? That puts the negative charges a little closer together. It's a little less stable. It doesn't like me anymore. And then I'm going to remove a water molecule. I'm going to do a dehydration reaction. Right, and move the double bond between those 2 carbons. Or not move it, but generate a double bond between those 2 carbons by loss of a water molecule. This is a lyase reaction, right? There's no redox going on here. But it also puts those negative charges in an orientation that is even less favorable than it was when it was tetrahedral. So it really doesn't like me now. And again, phosphoenol pyruvate, the thing I just generated, was the third of the 3 molecules. Creatine was our first. 1,3-bisphosphoglycerate above, and now phosphoenol pyruvate is the 3rd molecule that has more energy than ATP in that phosphate. So again, we'll lose the phosphate to ADP to generate an ATP. The double bonds rearrange slightly, and we have a pyruvate in the end. In fact, we're going to get 2 pyruvates in the end. So if we look at the overall mechanism here, our overall chart here, what's happening, starting with the glucose, right? We're adding 2 high-energy phosphates. That's going to cost me 2 ATP equivalents. And then in the end, I get out 4 ATP equivalents. Remember, I do everything at the bottom for 2 molecules. I lose 2 water molecules. I'm not so worried about that. And I generate 2 NAD pluses reduced to NADH. Okay? So that's my main goal, is to make those 3 products, NADH, the pyruvate, and the ATP. Okay? And a net reaction, I get 2 of each. So let's go through these steps one at a time, starting with step 1, and see what's going on. We won't go through mechanisms on every step, but a few of them we'll talk about some of the aspects of the mechanism. So in step 1, we have the enzyme hexokinase, which simply phosphorylates glucose. But it doesn't just phosphorylate glucose. It'll use any 6-carbon sugar. It prefers some over others, of course. It has a preference, a different Km for these sugars, but it likes glucose very well, so it has a very small Km for glucose. And if you look at the reaction, it shows it being reversible, right? It goes forward with a really long arrow there and a very short reverse arrow, and the reaction could be driven backwards. Given enough ADP and glucose 6-phosphate, you could drive this reaction backwards, but in the cell, that's never going to happen. Right? The concentrations aren't going to allow it in the cell. So we're going to say that step 1 is metabolically irreversible. It's just not going to happen in reverse inside the cell. Okay, so how does it work? Well, we said the carbon OH on number 6 is the most accessible, so we'll look at the bottom. You see how glucose shown here with its CH2 on number 6 and then the hydroxy sticking off above it. And the ATP is arranged in such a way, and I mentioned this last time in our last lecture, such that the magnesium is bridging the beta and gamma phosphates. And when the magnesium is bridging the beta and gamma phosphates, it tends to phosphorylate using or lose one phosphate. Whereas when it's bridging the alpha and betas, it tends to lose the pyruvate. So in this case, it's going to lose one. And what happens when the hydroxy attacks the phosphorus, right? We lose the bond between the two phosphates, right? The phosphodiester bond here, or phosphoanhydride bond here. And then the magnesium stays where it is in the active site, but the ATP shifts in the active site such that now the alpha and beta phosphates are bound to the magnesium, stabilizing this product. Right? And of course you end up with a glucose with a phosphate on number 6. Right? And then it lets both of them go. Okay, so it's a nucleophilic attack of a hydroxy group on a phosphate, and we lose the bond between the anhydride bond between the phosphates. Okay? And our products are glucose 6-phosphate and the ADP bound to the magnesium. Okay? So when does this happen in the cell? Well, as soon as glucose enters the cell, hexokinase will phosphorylate it. Now, what if we don't need to do glycolysis right now? The cell's always doing a little glycolysis, but what if it's not as necessary right now? We're well fed, we've got lots of ATP. I don't really want to burn all my glucose right now, but this is still going to happen. As soon as glucose gets in the cell, it is immediately phosphorylated. Yes, that's an investment of ATP that I may not get a return on until much later. But the goal here is I want to keep my glucose. So if a glucose is inside the cell, it's very unlikely to cross the membrane and leave. It's not a small molecule, it's very polar, right? But if I put a phosphate on it, it's infinitely less likely to leave, right? It's not going to, because it now has a larger structure, it's even more polar, and in fact it's charged, right? So that's never going to leave the cell on its own. So we're kind of keeping the glucose in the cell for later. So yes, it's an investment of ATP, but I'm going to get it back later. Okay, so why is glucose phosphorylated immediately upon entering the cell? So it will not leave. Okay, so once the glucose enters a cell, that's that cell's glucose. It will not leave, with the rare exception of maybe a liver or a kidney cell later. But if we're thinking muscle cell here, that glucose is never leaving that cell. At least not as glucose. Okay. So this enzyme is our classic case of induced fit. So what happens is ATP fits in the active site, finds its way and binds properly with that magnesium between the beta and gamma subunits. And upon binding of the glucose doesn't really have an active site that it fits very well. It's kind of not formed properly yet. But the glucose will not bind unless the ATP is already there, because it forms part of its pocket. The glucose binds, and upon binding, the enzyme changes shape. This is our classical induced fit. And it makes sense that it would be induced fit because this has to accommodate any 6-carbon sugar, glucose being the best fit, but any other 6-carbon sugar will do. So it has to be accommodating. So it can't just have a rigid, fixed active site like it would if it were the lock and key mechanism. Okay, so how did they catch this molecule in the act? Well, if you look on the right, you see they added ADP and glucose. The ADP binds just like the ATP would, except it doesn't have a third phosphate to lose. And so when glucose binds, expecting anthropomorphizing molecules here, I'm sorry, but glucose is expecting to gain a phosphate in here, and there isn't one to be had. So the whole structure just sits there stuck with nothing to do, and we catch it in the act. That's how we get a picture of it. Okay, so the ADP and glucose together can't do anything, and the enzyme just gets frozen there where it can't let anything go. And we catch it in the act like that and get crystal structures to show how this thing moved. And you see on the left it's more in an open face, and on the right it's more of in a closed or condensed face. Right, so hexokinase does phosphorylate glucose, but it isn't the only kind of hexokinase there is. Right? We have isozymes of hexokinase. What that means is they do the same chemistry, right? The exact same chemistry. They phosphorylate glucose, but they have different affinities for their substrates. So the glucose will bind to, say, hexokinase 1 differently than hexokinase 2 than hexokinase 3 or 4. They have a different affinity for each one, so the Km values are slightly different. And those occur in different tissues, and depending on the type of cell we have and how much glucose it gets exposed to regularly and how much it consumes that glucose. What is it using it for? It's not just glycolysis. So we need different hexokinases in the cell. All right? So we'll clump hexokinases 1, 2, and 3 together because they all have similar Km values, somewhere on the order of 1 micromolar to hundreds of micromolar, right? 10 to the minus 6 or 10 to the minus 4 molar. And then there's hexokinase 4, which is quite different from the other two. Its Km is 10 to the minus 2 molar, right? So that's much, much larger, right? And we call that one glucokinase specifically because it really is a lazy enzyme, if you think about it. It doesn't really go very fast. If you give hexokinases 1, 2, or 3 concentrations of glucose around their Km values, they're going to go at half maximal velocity. That's the definition of Km again. Right, so we got to remember these things. But glucokinase, hexokinase 4, at the 10 to the minus 4, 10 to the minus 5 concentrations, molar concentrations, that is nowhere near its Km value. It's going exceedingly slowly, right? If you get the concentration up to 10 to the minus 2 molar, hexokinases 1, 2, and 3 are already going near their Vmax. And if you add more glucose, that doesn't really change much at that end of the scale. However, if hexokinase 4 is given glucose around 10 to the minus 2, and then you increase it, it still has room or a range to go faster. Right? So that's why we have both of them. The only time hexokinase 4, or glucokinase, has anything to do, right? It's just sitting around and it's so slow, it's so weak at holding on to its glucose that the other ones consume all the glucose and turn it into glucose 6-phosphate before this one completes even a few, right? It doesn't have time to do anything. Until all the others are overwhelmed by a huge bolus of glucose, right? Say right after a meal, and all this glucose rushes into the cell. Hexokinases 1, 2, and 3 are overwhelmed by how much substrate there is. They can't go any faster. Well, glucokinase can pick up the slack because it says, well, you're busy with all of these other glucose molecules. I actually get a chance to do something. So it's there to respond to those large changes, sudden changes in glucose concentration. So hexokinases 1, 2, and 3 are sort of regulated, and we'll talk about regulation at the end. But glucokinase, or hexokinase 4, is not regulated at all. And the reason being is it's sort of self-regulating. It's only really active in the presence of large concentrations of glucose. So that's the only time we need it. So it kind of turns itself off because it's just not so active in lower concentrations. Okay. So we've made glucose with a phosphato number 6. And now we're going to take that glucose and isomerize it into a fructose. So at the top of the screen here, we have glucose opening up into the straight chain, right? Glucose 6-phosphate in a straight chain form. And from the shoulder down, from that third carbon down on each of these structures you see shown in black here, they're identical to each other, glucose and fructose, right? Even with the phosphate. The only thing we've changed here is move the carbonyl from carbon 1 to carbon 2. Right? So it's the same reaction we saw earlier when we were doing glucose to fructose during carbohydrates. There's just a phosphate on number 6 now, which is not involved. And then once we turn it into the fructose isomer, it will reform into the hemiketal form and make fructose 6-phosphate. Right? So this reaction is completely reversible, unlike the first one, because we're just making an isomer. The only thing I want you to remember about it, other than being completely reversible, is it will prefer to remain in the ring forms over the straight chain forms. That makes sense because the ring form is more stable. So I have to get over a slight hump to go from glucose 6-phosphate to fructose 6-phosphate. There is an activation energy. You have to turn it into its straight chain form. Not a very large hump, right? It's easy to do. And then it comes to equilibrium with the glucose and fructose forms. And then it's rather easy to turn back into fructose in its ring form because it's a downhill reaction. Right? But to convert one to the other, there is a slight activation energy required because they have to open it into a straight chain. Okay? What kind of enzyme, I forgot to ask you this, but what kind of enzyme or class of enzyme would step 1 be? Let's go back to step 1, our hexokinase. What class would this be?
Transferase.
Yes, it's a transferase. All kinases are transferases. They just transfer phosphates. So good. And step 2, this one's rather easy.
Isomerase.
Yes, it's an isomerase. Good. Right. And then step 3, it looks a lot like step 1. We're going to take our fructose 6-phosphate, the exposed carbon with the OH now, number 1, which wasn't so exposed before, is going to get phosphorylated in a very similar manner as step 1. Okay, this enzyme's a little more complex, it's a lot larger, has much more regulation, but it works the same way. We're going to take the phosphate off of the ATP and give it to the OH on carbon number 1. Okay, so I end up with a doubly phosphorylated fructose, a fructose 1,6 bisphosphate. Bis is another way of saying diphosphate. Okay, this is the key reaction for glycolysis. Right, this is the reaction that sets everything else in motion. This is where you control glycolysis. Okay? Everything happens here. So keep this in mind. This phosphofructokinase, or PFK, right? I'm calling it PFK. It's just an abbreviation for phosphofructokinase, but it's really PFK1. We'll see there's a 2 later. There's another version of this enzyme later. It's not an isozyme because it does a different chemistry. But we're going to call this one PFK1. Okay, it's the key regulatory step. We'll save the regulation for the end. Okay. What class of enzyme would PFK1 be?
Transferase.
Yes, it's our second transferase. Exactly. Okay. This arrow shows it going in backwards as well, but it's just like step 1. This is not going to happen in the cell. This we're going to consider irreversible again. So steps 1 and 3 in the cell we're going to consider irreversible.
Can you please explain again why it's irreversible?
So in the cell, we always have a flux through here. So we're going to have fructose 6-phosphate being generated by the previous step, and we're going to have fructose 1,6 bisphosphate being consumed by the next step. So we're always adding more starting material, we're always removing the product. So even if we could try to get this thing to go backwards, we'd have to add a large amount of its product and keep it around and continually remove the substrate, which doesn't happen in the cell. You can't get them in enough concentration using Le Chatelier's principle to drive this backwards. Now you can do it in a test tube, right? It's still not easy. You have to heat it up. But the cell has no way to manage that, to make that happen. So we're going to call this one irreversible as well. All right, we'll see the energetics of it, the numbers, a little later, and you'll see why it's so irreversible. Okay, so we take our fructose that's doubly phosphorylated, open it back into the straight chain form that's shown on the top left here, and then this molecule is going to get a divorce from itself. It's going to be split into 2 isomers of each other, right? And this reaction, if you remember back to your, I don't know if you learned this in first or second organic now, one of them, you did an aldol reaction. What we're doing here is a reverse aldol reaction. We're taking this molecule apart. So the top half is going to get the 3 blue carbons, the bottom half the 3 pink carbons. The phosphate goes on each side. And if we just cut it right down the middle between these carbons, it wouldn't be fair, because then the top would have a carbonyl and the bottom would not, which means they don't have the same number of hydrogens. Remember, a carbonyl represents a site of unsaturation. So if I were to cut it equitably right down the center between the carbons 3 and 4, then the top would have the bottom would have 2 additional hydrogens than the top. So if the bottom would give it 1 to the top, they would be equal. So that's why the blue hydrogen here is shown going with the top, right? And this is going to form a new carbonyl, right? So that gives us our aldehyde and our ketone that's formed as a product. Both of them having 3 carbons, both with 1 phosphate, all the same number of each components. Okay, so we have glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. The mechanism for this is quite complex. It won't be on your exam for this course, but if you want to look at it, we can talk about it after class. Right? But it's a reverse aldol reaction. That's the chemistry. What class of enzyme is this? What kind of chemistry are we accomplishing?
It's a lyase.
It is a lyase, right. You might think it's a hydrolase at first, but it's not. I'm not adding a small molecule and breaking a sigma bond. What I'm doing is breaking that bond, and I'm not doing any kind of redox. If you want to count, you can check that it's not redox. But I am making a double bond right here. I'm making that aldehydes double bond. So am I making or breaking a double bond? Yes. Am I doing so in the form of a redox reaction? No. Right? So did I add a small molecule to break this sigma bond? No. So it's not a hydrolase, it's not an oxidoreductase. That leaves us only with a lyase. So it's our first lyase of the pathway. Okay? And then, of course, the next step is rather simple. We're talking about converting the dihydroxyacetone phosphate into the glyceraldehyde 3-phosphate. They're isomers of one another, and this looks almost exactly like we did back in step 2. We're converting an aldehyde into a ketone, or a ketone into an aldehyde. It's exactly the same chemistry. The only difference is, from the shoulder down, there's only 1 carbon this time instead of 4. So if you look back at step 2, it is nearly identical to step 5. The substrate is just shorter, right? And this has one of the best names of any enzyme because it's actually named for both directions simultaneously. And isomerases are easy to do with that. They're both trioses, they're both 3-carbon sugars with a phosphate. So triose phosphate isomerase. You named both of them at the same time and called it an isomerase. You can't have a better name for an enzyme. Okay. Right, so now that we've made 2 moles of glyceraldehyde 3-phosphate, let's see how we can recover the energy we've invested, and then some. Okay, so in step 6, we're going to take glyceraldehyde 3-phosphate and phosphorylate it one more time. And at the same time, we're going to oxidize it. This is the only redox step in the entire pathway. Okay, so of the 10 steps, step 6 is the only redox. Okay? We're going to put a phosphate on, but we're not going to use an ATP. This is important, that we do not use another ATP to invest that phosphate. We're going to just grab a phosphate floating around in solution. There are plenty of them around. Right? So we take the phosphate, the glyceraldehyde 3-phosphate, it already has 1, and we're going to do 2 things to it. We're going to oxidize the molecule, and then we're going to put the phosphate on, right? All in one reaction. Okay? It's 2 steps, but it's 1 reaction. I hate to use the word step there. It's 2 parts of the same enzyme's function, so we just call it that way. Okay? So if we were to try to do this in 2 separate parts, and you take the glyceraldehyde 3-phosphate and oxidize it, you would turn your aldehyde into a carboxylic acid, right? You'd have 3-phosphoglycerate, which would be very stable. That'd be a very favorable reaction to do, and your product would be very stable, it'd be great. But then you could never put the phosphate on, because that would be very unstable, very unfavorable thing to do, right? You're not going to put a negatively charged phosphate on a negatively charged carboxyl group, right? It just doesn't seem like it's going to happen, and it wouldn't. Okay? So what this enzyme does is it couples those 2 reactions. It takes the very favorable one and drives the unfavorable reaction. We talked about this last time, how we use an unfavorable or a favorable reaction to drive an unfavorable one. Okay? So in these 2 steps, here they are shown at the top. If they were to occur in isolation, the top step takes the glyceraldehyde, right, and oxidizes it to a carboxylic acid. Okay? At the same time, if you oxidize something, you must also reduce something else. Those electrons have to go somewhere, right? So the electrons from this, from the aldehyde here, go to the molecule of NAD+, both electrons and one of the protons, to make NADH. Right? The other proton is lost to the solvent. Right? So to turn an aldehyde into a carboxylic acid, of course, you need a water molecule to provide the other OH that attacks the carbonyl. Right? And then we end up with a carboxylic acid. Wonderful. We got an NADH out of it. We'll talk about what we do with those guys later. But this is very stable, and that would be the end of this reaction. You couldn't get anything else out of it. And we would move on all the way to step 8 at this point. But we don't want to do that. Right? We'd rather have this carboxyl group also accept a phosphate, which is not favorable at all, as you can tell. Right? So I couple the 2 together. And this is a very unusual thing with enzymes. Not unusual to be coupled, but the way in which it does it. If you were to follow these 2 steps, this first one and then this second one, on a reaction progress diagram, remember this from our talk on enzymes, it's the progress of the reaction, not necessarily time, and then the free energy, or we replace this axis with instability. Okay? So we start somewhere, and we end somewhere else, adding an enzyme does not change these points. Where we start and end are based on these structures, the beginning and the ending structures. It has nothing to do with the enzyme. Enzymes do not change delta G. Okay? Now, what they're showing here in the center is the activation energy. You go up where it says oxidation. We have an activation energy to get over, and then it goes very low. That's the result of this first step. First step of oxidation, if we were to do these stepwise, would fall into this deep pit. Right? And then to do the second reaction, we have this huge hill to climb, the acyl phosphate formation reaction. We'd have to climb over this huge activation energy to form our products. Right? They're calling it delta G double dagger here, or it looks like plus plus, but it should be a double dagger. We didn't want to call it that because I didn't want to confuse you with the G in there. This is just activation energy, right? You can rewrite that as EA if you want, activation energy. Just another way of labeling it. It means the same thing, but it is not the delta G of the reaction. Okay, so we don't want this to be so large. And I remember you guys told me back when we talked about enzymes that what do enzymes do? They lower the activation energy. Well, that's one thing they can do. Here, they're not really lowering the activation energy at all, right? In a sense. What they're doing is taking this very stable intermediate and decreasing its stability. Okay, so instead of having to fall in this pit, right, it follows a much smoother path. So we have our enzyme over the first, I'm talking about panel B over here now. We go over the first activation energy hump, but we don't fall in a large pit. So instead of letting this thing go as just a carboxylic acid, we hold on to it by the enzyme with a sulfur. Right? It's going to be made a thioester. And thioesters are not as stable as regular old esters. So instead of being deep in this pit, it's much higher up. So you can see the path getting through here is not so difficult anymore. The second increase, the second hump is easy to cross. It's not this huge hill you have to climb now. So what this enzyme is doing is coupling these two half reactions into a single reaction, making one rely on the other to drive it forward. But I'm not decreasing the activation energy per se. I'm raising the energy of the intermediate molecule so it doesn't fall into an energetic pit. Okay, so let's see how it does that. Okay. Oops. See how it does that. Sorry, I don't have a slide for that one in this set. But what we're going to do is have this molecule, right, bind to the enzyme. And instead of having a water molecule attack this, we're going to have a sulfur from the enzyme attack this. Okay, so instead of having a water molecule come on and release it as a carboxylic acid, we'll have a sulfur attack here and it's holding on to it for a while. It's not going to let it go. The enzyme is getting covalently involved. Right, it should sound familiar. And then we'll have another molecule, a phosphate, come along and say, I'll take that off your hands. Right? You don't have to hold on to it with the sulfur anymore. The phosphate can take this molecule off your hands and regenerate the enzyme. What kind of reaction scheme am I talking about here? If we think back to our mechanisms, what am I referring to?
Is it the nucleophilic attack?
Well, nucleophilic attack is the step that's happening, it's the chemistry that's happening, but what type of mechanism is this? We had ordered sequential, we had random sequential, we had double displacement.
Ordered sequential?
Are both substrates on the enzyme at the same time?
No.
No. Our two substrates are what? Well, in fact, we have three substrates, but our substrates are the glyceraldehyde, right, and the phosphate. And they're never there at the same time. Remember,
Double displacement?
It's double displacement. The enzyme is getting involved. There's an enzyme intermediate right here. Right? So we have two half reactions. This is your classic double displacement. Right? So one substrate shows up. In fact, there's two substrates at the beginning. Right? Does some chemistry. One or more products leave, which is true. And then the second substrate shows up. In this case, it's a third substrate, but a second set of substrates can show up and interact with the enzyme, relieving it of the parts that we're holding on to, and the other products leave. This is your classic double displacement mechanism. It just has an additional substrate. If you were to try to put it in its normal form, instead of being a bi-bi type reaction with two reactants and two products, There's in fact 4 reactants and several products. So we name them something else, but it's still double displacement. Okay? So what we do when we're done is we've ended up with this rather unstable molecule. Right? It's one of our 3 molecules that has more energy than ATP, and because of coupling this oxidation reaction, we're using the energy from that oxidation to drive the formation of ATP in the next step, okay, by making this very unstable thing. Right? So here it is. This is an unstable beta-keto arrangement. I know this phosphate's not drawn out for you, but if you draw it out, this phosphorus atom has a double bond to one of these 3 oxygens, which means there's a double, single, double bond arrangement, which is beta-keto. That's not stable. The easiest way to resolve that is to send the phosphate hiking. All right, so you're out of here. I'll give you to an ADP because I have more energy than the ATP molecule you create. And so it goes in the forward direction. But it's not much more energy. It's almost the same, right? The energy formation here is on par with ATP. Even though we say this one has more energy than ATP, it's not much, right? So we could have this go completely in reverse. So what drives this reaction forward then, if we know it goes forward during glycolysis? So if I tell you that the overall delta G of this one is near 0, so how does it go forward?
The product's used in another reaction.
Yeah, the product is going to be used in the next step, and the previous step is going to generate more substrate here. So it's Le Chatelier's principle, right? We're going to drive it forward if we consume the product and supply more starting material. We could also drive it in the reverse reaction by the same principle. We could consume the 1,3-bisphosphoglycerate in another reaction, and we could generate more 3-phosphoglycerate somehow. We'll see that in our next lecture. But this thing is totally reversible. Okay? So looking back at step 6, I told you it was a redox reaction. It was the only one. What class of enzyme is step 7 here?
I'm sorry, did you say it was reversible or irreversible?
It is completely reversible. Right, so far, our only irreversible steps are 1 and 3. So what class of enzyme would number 7 here be?
Transferase.
It's a transferase again, exactly. And it's transferring yet more, another phosphate. So it's a kinase. Unfortunately, for you, the name might be a little confusing. So it says phosphoglycerate kinase. It makes it look like it's describing the reverse reaction, and it is. But the overall trend is when we have kinases, we tend to name them, whether it's reversible or not, we tend to name them in the direction that consumes the ATP, even if it won't go that way. This one can go either direction, so name's not a big deal. But you see how it's named for the direction in reverse, as if you're phosphorylating the 3-phosphoglycerate, right? That's not what this enzyme is really doing in the forward direction. That's the reverse operation, but that's its name. We always tend to name it in the direction in which the ATP disappears, okay? Whether it's the direction we intend or not. Okay? And that way we keep calling all of them kinases. Okay? So the other question I have at the bottom is similar to the last one I asked you. It says, why does the steps equilibrium toward the right when ADP is more stable than ATP, clearly, by 7.3 kilocalories per mole? This has nothing to do with Le Chatelier's principle. Why does it prefer to the right over the left? And I know ADP is more stable than ATP.
Because you aren't dealing with the unstable beta-keto arrangement.
Right. So the 1,3-bisphosphoglycerate compared to 3-phosphoglycerate is more unstable than ATP is compared to ADP, which was in our chart from the last lecture. Right. So the destruction of the beta-keto arrangement and the separation of those charges is a better impetus than ATP losing a phosphate. Right, that's the reason. Okay, so how many molecules of ATP have been formed at this point when we finish step 7?
2.
2. Remember, we do this for 2 of these molecules. We're starting with 1 mole of glucose, so we have 2 moles at this point. So how many have been used or invested? How many ATPs have I put into this so far?
2.
2. So we've kind of broken even at this point. Good thing we coupled that last reaction, or we wouldn't have gotten these out of it. Right? So that coupling in that last step is providing the break-even point here with 3-phosphoglycerate. Had we not done that coupling, we would have still arrived at 3-phosphoglycerate, and we'd have not gotten any ATP out of it. Okay, so what do we do now? We have a very stable molecule in 3-phosphoglycerate. The charges are as far apart as they can get, right? There's no beta-keto arrangements, so it's very stable. So I want to make it a little unhappy with me. All right, so let's finish up steps 8 through 10 here in one big go. So we're going to take our 3-phosphoglycerate and make it a little less stable. We're going to move the phosphate from its position on carbon 3 up to carbon 2. Now, this is just a swap. We're going to switch the H in the phosphate, rather simple. Right? What class of enzyme would this be?
Isomerase.
Yes, it's yet another, it's our 3rd isomerase we've seen. It was back in step 2 and step 5, which are nearly identical reactions. And here's another isomerase in step 8. Except this one's not like the first 2. We're not just moving double bonds around, right? And hydrogens. Here we're moving a big group. We're moving an entire phosphate molecule. So if we move something bigger than a proton, right? If you're just moving protons around or hydrogens around, we're still not going to call it a mutase. It's just a generic isomerase. This is still an isomerase, but a subcategory of isomerases where you move something bigger than a proton, we're going to call mutases. Are we moving something bigger than a proton? Yes, we're moving a whole phosphate. If we moved an amino group or if we moved a methyl group or anything like that, it would also be called a mutase as long as we're making an isomer. So all mutases are isomerases. They're just a subclass of isomerases in which you move something bigger than a proton. Back in steps 2 and step 5, the only thing we moved around, it looked like we moved double bonds, but double bonds are just electrons. Well, we moved around were protons, right, in our shuffling to make the aldehyde into the ketone or ketone into the aldehyde. But like most isomerases, it is again completely reversible. So again, the only things we've seen that are irreversible are steps 1 and 3 so far. Okay? So back to our story, we had a phosphate on number 3, and I've moved it up to number 2. I've taken the double bond, or sorry, the negative charges and moved them closer together. Okay, so now the negative charges are closer together. The molecule doesn't like me as much. Right? So now I want to make it even more mad at me. So I couldn't do this before, but I can now. I'm going to remove this OH, the OH that's on carbon number 3, and the H that's on carbon number 2. Right? If I remove the H and the OH between those two, that'll be water that's leaving. And if I lose a bond to each of those things, I'm going to get a double bond between the carbons. So I'm going to make an alkene. So at this point, what has happened around carbon number 2? It's got a carboxyl group attached to it. It's got a phosphate attached to it. And now it still has those things attached, but it's got a different geometry now. So what's changed about carbon number 2's geometry?
From tetrahedral to trigonal planar?
Right, we've gone from tetrahedral up here, 4 single bonds to it, to 2 singles and a double, so it's a trigonal planar arrangement. And trigonal planar means what it says. It's planar. So what does that mean? That means all 6 of these atoms are in the same plane. So that would mean the 2 carbons and the 4 things they're directly attached to. The 2 hydrogens, this carbon, and this oxygen. Right? So all 6 of those atoms are in the same plane because both of these carbons are trigonal planar now. Because they're in the same plane, that puts these negative charges, the phosphate's 2 negative charges and the carboxyl group's negative charge, actually closer together than they were as a tetrahedron. Right? So now it really doesn't like this arrangement. Right? So we've put the 2 charges closer together in the first step, step 8 here, In step 9, we put them a little closer together, but I've done one other thing it really doesn't like. I've created another beta-keto arrangement, right? Now, the carboxyl group relative to this new alkene double bond is alpha keto. That's favorable. But the phosphates double bond and this carbon-carbon double bond are again separated by 2 single bonds, so it's beta keto, just like before. So if you had to resolve the situation, which is the best to do? Do you lose the phosphate or do you lose the carboxyl group as CO2? What do you think is a better choice?
Phosphate.
Yeah, if I lose the CO2, I still have a beta keto arrangement, and I've lost an alpha keto. That doesn't sound favorable at all. So if I lose the phosphate, I retain the alpha keto arrangement, and I lose the beta keto one, and I also lose those negative charges. So this is the most favorable you can have. So again, this is one of our 3 molecules, more energetic than ATP. So the phosphate is going to leave and go on an ADP molecule. That's going to leave behind this carbonyl, not carbonyl, but alkene, right? And the alkene is not very stable like that with an O minus, so it's going to collapse to a carbonyl, and the carbon-carbon double bond is going to go down to the lower carbon, carbon number 3, and it's going to pick up a proton, obviously, because CH2 minus is a very strong attractor of protons. So we'll end up with a methyl at the bottom. So now I have an alpha keto arrangement with a methyl group called pyruvate. All right, very, very simple resolution. Back to step 8, you told me that was an isomerase. Step 9 is a what? What am I doing in step 9 with enolase? What class would that be?
Lyase as well.
Right, it's our second lyase, right? So am I making or breaking a double bond? Yes, I'm losing this water molecule and turning an alcohol into an alkene, right? And I'm making an enol, right? So this would be the ene, right? And then the OH would be on there, right? Or over here we have the dihydroxy, right? So I'm turning a diol into an enol, right? So that's your typical conversion you see, and it's a lyase function, losing the water. Again, totally reversible, because this is not stable at all. Water could enter this and turn it back into 2-phosphoglycerate rather easily. But we don't stop here. We drive it along to pyruvate using pyruvate kinase, right? And this step would be what class? Step 10, the last one, would be what class?
Another transferase.
Right, it's our 4th transferase. And again, a kinase, right? Everything we're transferring has been phosphate. So all 4 kinases have been, all 4 transferases have been kinases. So we transfer it to make pyruvate. This step is our 3rd one we're going to consider irreversible for the same reasons. Okay, so of the 10 steps, we had 3 that we're going to consider are completely irreversible. Steps 1, 3, and 10, all of which happen to be transferases or kinases. There was a 4th kinase at step 7, but that one we said was reversible. So it's the only reversible kinase in this pathway. Okay, so let's put all that together and see if we can make it make sense. We did 10 reactions, but I'm going to simplify it for you. There's really only 4 types of reactions going on here. Right? We had some kinases, those transferases we talked about. We had 1 redox reaction take place. That was over at step 6. We had 3 isomerases. 1 happened to be a mutase, but we did that 3 times. And then we had 2 lyase reactions. So if you can just remember, there are only 4 types of things going on here. There are 6 classes, which 2 are not represented at all.
Hydrolases.
And?
Ligases.
Right. We didn't make any new carbon-carbon bonds, right? So there was no ligases here. And we didn't break any carbon-carbon bonds that weren't a lyase. Right? So we didn't add a small molecule and break a bond. So there's no making and breaking of carbon chains except for that one that is a lyase instead. So no hydrolase, no ligase. Another way to remember this. Another thing you can remember is there's 1 redox reaction, there are 2 lyases, 3 isomerases, and 4 transferases. 1, 2, 3, and 4 of those classes. If you add 1, 2, 3, and 4, you get 10. Right? So the only thing left to remember is the order in which they occur. And if you remember the story of what happens, you can remember what each class can be, right? So we take glucose, we add a phosphate, that's going to be a transferase. We turn it into fructose, isomerase. We add another phosphate, there's our second transferase. That molecule splits from itself, that's going to be the lyase. We convert one of its products into the other, that's an isomerase, that's our second one. And then we oxidize it, that's the only oxidation step in the whole thing, right? Our one redox reaction. Then after we put the phosphate on, we take it right back off and give it to ADP. Well, that's our third transferase. And then we take the 3-phosphoglycerate that results and move the phosphate. Well, that's our third isomerase. That's the last one. That's the mutase. And then we take the water molecule away in the form of an H and an OH to make phosphoenol pyruvate, a very unstable thing. Well, that's our second and last occurrence of a lyase. And finally, the phosphate comes off and forms another ATP, leaving us with pyruvate. That's our fourth and last transferase, or kinase. If you can tell yourself that short story, you don't have to try to memorize everything. Learn this in layers. Learn little pieces and layer it on each other. So telling yourself one layer will remind you what's in the next layer. Okay. The slide on the image on the very right where it says gluconeogenesis, we'll deal with that in the next lecture, and we're going to refer to this again. But glycolysis on the left, all the red ones, 10 reactions, only 4 classes. Just tell yourself the order in which they occur with a little story. Okay. So let's look at the overall reaction. We started with glucose, right? We had 2 ADPs, right, invested. We get out of it 4 ATPs, right? But only 2 net, so we subtract 2 from each side. This is the net equation, so we don't write the same thing on both sides. If there's 2 extras, we simplify it. 2 NAD pluses were converted to NADHs, those were at step 6. And then we had 2 phosphates we needed extra to put on those ADPs to make the ATPs. In step 9, we got those 2 excess water molecules, and in step 10, we generated our 2 pyruvates. This is the net reaction. So overall, what did I get out of it? I got 2 pyruvates, 2 ATPs, 2 NADHs, 2 water molecules. I think we can ignore the water molecules. And we're going to ignore the protons because they don't do anything. Right? So what we really get out of it that we're concerned with are a pair of pyruvates, a pair of ATP molecules, and a pair of reduced NADHs. Okay? We'll see what we deal with those NADHs later. Okay? So looking at the bottom, all the net reactions here are the reactions of glycolysis. I want you to focus on the numbers on the far right. Right? So we'll look at it in kilocalories per mole. On the very far right column, this is the delta G. The column next to it is the delta G naught prime, which means under standardized conditions, this is what the delta G would be. This is not what happens in the cell. In the cell are the conditions on the far right, the true delta G. Right? So at the far right, we'll look at those numbers. 3 of them should stand out to you as different from the rest. Right? So looking at the ones on the right, which 3 stand out as drastically different from the rest?
The 3 positive ones?
No. The 3 positive ones are still near 0.
Steps 1, 3, and 10.
Yeah, steps 1, 3, and 10. I mean, you're right, they are positive, I agree, but they're not much different than the other ones who are also very slightly negative. But steps 1, 3, and 10 are double-digit absolute values. None of the others are even close to that. In fact, these are, 16, 22, and 33, right? So having such a large and negative delta G means what?
They're irreversible.
Right, they're irreversible in the direction indicated. Right, so since it's negative, it tends to go in the direction forward, written, and since it's large, it's irreversible. If I had something that says plus 30 as a delta G, that's also an irreversible reaction, but it tends to go only in the other direction as compared to what is written. That's what that means. So all the other ones, though, whether they're positive or negative, their absolute values are small, which means they're reversible. Okay? And even so, if you look back at the delta G naught primes there, which is under standard conditions, step 2 would rather turn into glucose 6-phosphate. Right? It doesn't want to go to fructose 6-phosphate. But under conditions in the cell, it's slightly negative now because there's an excess of glucose 6-phosphate and not so much fructose 6-phosphate in the cell. So we're driving it forward. And in fact, look at step 1. It's negative 16.7 under standard conditions, so it won't go backwards under normal concentrations or equivalent concentrations. But in the cell, it's twice that negative. It's almost double the number, which tells me that the amount of glucose in the cell far exceeds the amount of glucose 6-phosphate at any point, because we're consuming the glucose 6-phosphate in the very next steps. Not just this one, but others we'll talk about. Right? And the reason step 10 is so negative, look at its delta G naught prime, negative 31.4. That's because of that elimination of the beta keto group, right? And separating of the charges and moving the double bond to a more electronegative atom. All those are very favorable things. But in the cell, it's only negative 16.7. It's about half that, which tells me there must be a lot of pyruvate in the cell compared to phosphoenolpyruvate, which is true. Do I want you to memorize any of these numbers? No. I'm illustrating the point of why we're going to consider those three metabolically irreversible. They don't go backwards in a cell. Okay? And thus, that's the three we need to regulate. If you want to control a pathway, you don't control it at a reaction that's reversible. You want that flux to go through whichever direction is possible. You control it at an irreversible step, preferably early in the pathway. Okay? So what happens to pyruvate afterwards? We'll get to the regulation in just a second, but what happens to pyruvate afterwards? Well, we can do three things with it. If I want to continue more glycolysis, I'm going to need some more raw materials, right? So to continue glycolysis, I'm going to need more glucose, and I'm going to need one more thing, an NAD+, because I consumed it in that previous step 6. So to continue, I need to turn my NADH I just made back into NAD+. Right? And the only way to do that is to oxidize it, right? NADH to NAD+ is an oxidation. And if you're going to oxidize something, you must also reduce something else. So in the simplest case here, in the very center, we take pyruvate and we reduce it to lactate, right? This is not lactose, this is lactate, or lactic acid is the conjugate acid of it. But NADH in the process gets oxidized to NAD+. It's donating the electrons back to pyruvate and making lactate. The point of that wasn't to make lactate. The point of it was to regenerate my NAD+, so I can do more glycolysis. That's assuming I'm supplied with more glucose. The other way we can do that is we take pyruvate, and you remember the structure of pyruvate. It's got 3 carbons. It's got a carboxyl group on top, a carbonyl in the center, and a methyl group on the third one. We lose the CO2, that's clearly the top carboxyl group, and that leaves us with a 2-carbon aldehyde, right, or acetaldehyde, right, or ethanal if you want the IUPAC name. And then we can take an aldehyde and reduce it to a 2-carbon ethanol, and at the same time oxidize our NADH back to NAD+. Once again, regenerating our NAD+, so we can do more glycolysis. In both of these cases, lactate and ethanol are byproducts. They're not the intended goal. The goal was to regenerate NAD+. So the lactate and the ethanol are just useless byproducts. They're dead-end molecules for these cells, right? So we just release them into the environment. So if you're a yeast or a bacterial cell, a microorganism, you just release the CO2 and the ethanol as byproducts. Humans have come along and understood that chemistry and said we can make use of that. We use the CO2 to make bread, and we use the ethanol to make alcoholic drinks. It's our 2 oldest chemical reactions, right? In the sense of a muscle cell, perhaps, or a red blood cell, or even brain cells, we can't do that because we don't want to release a lot of CO2 or ethanol there to kill other cells. We turn it into lactate. It's a dead-end molecule, but I get my NAD back. And I'll send the lactate off to New Jersey. That's an inside joke, because New York sends all their trash to New Jersey. Right? So the cell's going to send all their lactate somewhere else, and you deal with it. Right? So the lactate will be sent to the liver, and the liver will deal with it. In the last case on the right, pyruvate will lose the CO2 once again, but instead of making acetaldehyde, we couple it to something. Right? So we're going to take that acetaldehyde molecule, oxidize it once to a carboxylic acid, right? That further exacerbates our problem of NADH, because we're going to consume another NAD there. That's not helping us. But we're going to attach it to a molecule called CoA, right? And we'll talk about that one on Tuesday. And then with that, acetyl-CoA can then enter the mitochondria and become the substrate that starts the citric acid cycle, right? Which will again exacerbate our problem of NADH. Right? So we'll talk about those next week. But for today, we want to finish all the regulation of glycolysis. Okay? Briefly, let me go through these. I think we said this chemistry. I just have slides for you to read it to yourself if you want. Pyruvate, losing a CO2, becomes the aldehyde like I described. Reduce it once to ethanol, oxidizing NADH to NAD plus by alcohol dehydrogenase and releasing ethanol as a byproduct and CO2. The graph at the bottom kind of shows you what the purpose of this is back in step 6, we turned NAD plus into NADH, and now in this fermentation, we turn NADH back into NAD, regenerating it. So the net reaction now doesn't contain any NADs. It's glucose gets converted to 2 ethanols and 2 CO2s and a pair of ATPs. Right? So we've got a net reaction that sums up our fate of our glucose atoms, right? And we get total of 2 ATP out of it. We didn't get anything extra out of this reaction, no additional ATPs. We just regenerated the NAD to make it a net reaction. Right? Here's the one to lactate. We don't lose the CO2 this time. We simply turn the pyruvate, reduce it once. The carbonyl here becomes a secondary alcohol, right? And you get lactate, right? I don't get any more ATP out of this, but I do regenerate my NAD+, just like the other one. Right? And this lactate, of course, then goes back to the liver, and the liver turns it back into pyruvate and into glucose for me, right? And we'll talk about that next time as well. It's called the Cori cycle. Okay, so here's the example of that. Glucose turning into 2 lactates. I still get 2 ATPs out of it, but lactate's a dead-end molecule. I got to send it to the liver and turn it back into glucose, which in fact is going to cost me far more than 2 ATPs. It's going to cost me 6 ATP equivalents. Okay? So you're borrowing from the future at 300% interest. Okay. All right, and lastly, the third one, which we'll cover next week, it takes pyruvate and oxidizes it once, losing a CO2 to make the acetyl group, not aldehyde, and putting it on CoA. So this made my problem worse. I did not regenerate my NAD. In fact, I used another NAD, right, to make NADH. So this could be a problem, right? Some examples of these organisms that do this obligate anaerobe type chemistry. If it begins with Clostridium, this is a very bad genus. We have Clostridium tetani, which causes tetanus, Clostridium botulinum, which causes botulism. Perfringens is a gas gangrene. Perforin means to perforate, right? So this organism gets a little membrane around a group of them, right? And then they release all this CO2, which can't get out, and it swells up. Your leg becomes the size of a watermelon, and it's full of CO2 gas, and at some point it tears the tissue, right? So it perforates the tissue, which is bad. Bartonella, which is cat scratch fever, and Bacteroides fragilis, which causes blood infections and abdominal pain. So all these organisms do this anaerobic metabolism. So in the absence of oxygen, this is how they regenerate their NAD+. So these are very bad infections. Okay. Other than glucose, we can have some other sugars enter the pathway, right? We had some other carbons that could do it. We have galactose, which is a cousin of glucose, fructose, another isomer of glucose. So if we eat galactose, right, we can easily convert it to glucose 6-phosphate, right? So if you have galactose, you first phosphorylate it. Hexokinase can do that. Remember, it works on any 6-carbon sugar, just prefers glucose. But if you have galactose there, it will do it. It'll make galactose 6-phosphate for the same reasons. And then we convert galactose 6-phosphate to glucose 6-phosphate. Yet another isomerase would accomplish that. Okay? If you eat fructose instead, we can phosphorylate fructose, make it fructose 6-phosphate, and it's ready to go. It's at step 3. Okay? So all these other sugars can enter our glycolytic pathway just by a slight isomerization. Okay? Where do we get galactose? Well, you get it from, in mammals, we get it from lactose, right? This is not the same thing as lactate. Make sure you know those two apart. So lactose was a disaccharide made of galactose and a glucose with that beta 1,4 linkage. Right? So if we break that apart and we get a galactose and a glucose, they could both enter the pathway. The glucose being a more favorable food source, but it can also use the galactose as well. Right? So what happens if you can't digest that lactose? Right? So here's lactose showing there aren't extra carbons here. This is that weird drawing again. But it's a beta 1,4 arrangement. So what if you intake lactose sugar, but you can't digest it, right? We call those lactose intolerant, right? So if we were normally in class, I'd ask the audience to raise their hands. You don't have to participate if you don't want to. But usually you get a hand or two that goes up and they say they're lactose intolerant. And those of you who are normal. The rest of us who are lactose tolerant are mutants, right? With no superpowers involved here, but we're mutants. At some point in history, generally in the Scandinavian peninsula here in Northern Europe, it happened elsewhere in the world as well, but this is the known source for this mutation. The winters were very cold, right, during the last ice age, right? Very, very cold winters. Humans lived there, and they had domesticated animals at that point, mostly mammals, like goats and sheep and cows and stuff like that. And if you survived the winter, you had to subside on those animals' milk, right? And if you couldn't digest it, you either had a very bad winter or you died of starvation, right? So many, many years of that, and only those who could digest the milk survived, right? So it's a very cruel selection mechanism. But because of our domesticated animals there, the only people who survived the winter were those who were lactose tolerant. They gained a mutation, right? So if you think about why are we just lactose tolerant all the time? Well, that would make a mother's life difficult. So for a mammal, one of the key hallmarks of being a mammal is we produce lactose, sugar for the newborns. And at some point you want to stop feeding them, the mother's milk and have them eat their own food. Well, a great way to do that is to make them unable to digest the milk, because they do that a few times and they're going to change their mind about breastfeeding versus going and eating their own food, because that wasn't very fun anymore. It was, I'm having indigestion, I'm having to go to the bathroom all the time. This isn't good. I'm just going to eat my own food now. So it's weaning the newborns or the offspring off of mother's milk by making it indigestible. And the way they do that is the lactase enzyme, at some point after birth, it depends on the organism, but could be months to years later, right? They just stop making it. The production in lactase drops tremendously. So you can't digest the lactose, and that meal doesn't become fun anymore, right? So you can't digest it. You're not getting anything out of the milk. You're just having to run to the restroom. So you just wean them off of that food source. Well, those of us who are lactose tolerant, it doesn't go down, right? You keep maintaining a high concentration of lactose. The trigger to turn it off was eliminated because of the need for the food in those cold winters. Okay? So what's the problem with that? Well, later on in life, even if you're lactose tolerant, that production of lactase will fall off as you get, in your 60s and 70s and 80s, especially by the time you're 90, right? And that could be a problem for all of you future physicians out there. Listen to this. When you have patients going to the physicians now, right, like your grandmother or your great-grandmother, their entire life they've been told what?
Milk is good for your bones.
Drink your milk, right? Because they're trying to stave off osteoporosis. Keep drinking your milk. Drink your milk. Drink your milk. It's what they keep telling them. And it's not bad advice when it comes to staving off osteoporosis. However, you're going to stop digesting the lactose. And so in the blood, we're going to have a high concentration of lactose, and eventually it will hydrolyze and become galactose and glucose, of course. But it's not as efficient as if you had a lactase enzyme. So there's going to be higher concentrations of these sugars in the blood, right? Higher concentrations of glucose in the blood, not a problem. Glucose is very soluble. However, galactose, because of the change at number 4 there, the OH being up instead of down, is not as soluble in water or in blood as glucose is. So if the galactose concentration rises, you've done this when you were a kid, when you take sugars and get them at really high concentrations and then let it start to dry out, you're going to make sugar crystals, right? It crystallizes. Well, the same thing is going to happen in the blood. And it's not such a big deal in most blood vessels except the ones that are here, right? Because those blood vessels are very, very tiny. And when the galactose, basically syrup, going through it, right, crystallizes, it has nowhere to go. So you get what's called a cataract. There's many other types of cataracts, but this is the one from crystallized galactose. So galactosemia causes these type of cataracts, and it's like looking through stained glass all the time. You can't wipe it off. It's in the lens itself, right? Now you could have an entire replacement to get rid of the cataract, but if you don't stop consuming all that lactose, you're going to get more of it. Okay? So we have a new solution. Have them drink their milk. It's mainly to get the calcium, but let's get the milk without the lactose. We have that now. We didn't have that 70 years ago when they were prescribing this milk all the time, right? So when your patients are getting elderly, yes, still drink your milk to keep the calcium in there, but let's get the non-lactose milk, right? Or get calcium some other way now. That's the main idea now. So be careful what you tell someone to do, because you might be promoting cataracts formation. All right, let's finally do our glycolysis regulation. So these charts might seem daunting at first, but I want you to picture it from a logical standpoint. We're going to regulate it at 3 steps. Which 3? The irreversible steps. 1, 3, and 10, because they have large negative delta Gs. Okay? So looking at the slide, or the picture on the left, this is at rest. Cells are happy, they've got lots of ATP, they're not doing anything, they don't need to do a lot of glycolysis right now. So how do we turn glycolysis off? Well, we're going to regulate it at 3 steps. Number 1 is sort of self-regulating. We really don't regulate it that much. It's kind of a feedback regulation. Hexokinase will bind its product, glucose 6-phosphate, and that turns it off. So if its product far exceeds its substrate, they compete for the same binding site. This is negative feedback inhibition, very simple. Then it'll just slow down, right? So it just turns glucose into glucose 6-phosphate until it shuts itself off. And if more glucose were to enter the cell, it turns it back on again because the glucose finds its way to the active site. So it's a very simple negative feedback product inhibition type thing, right? So that one's trivial. The other 2 are more complex. So the next one, step 3, PFK1, is regulated at a site distant to the active site. That's an allosteric site, right? And what binds there is a molecule of either ATP or AMP. It's a pocket that binds an adenine molecule with 1 or 3 phosphates on it, right? So if it binds there with 3 phosphates, ATP, it turns the enzyme off. They give it as a power button on the enzyme. It's not in the active site. I know ATP also binds in the active site. It's a substrate, I agree. But this is a separate binding site for an adenine-like type molecule. If ATP binds in that site, then the enzyme's off. It doesn't work. If AMP binds in that site, it's on. One of them will always be bound there, right? Because they're always in the cell. So it's detecting the ratio of ATP to AMP in the cell. If AMP is low and ATP is high in the cell, ATP is more likely to bind there, and it turns off PFK1. Okay. If AMP starts to rise because we're running out of ATP, and ATP starts to drop, then we're over in the situation on the right, where the AMP is large and ATP is a small concentration, then AMP tends to bind there, and that turns PFK1 on. And that should make sense. If I have ATP, stop making more. If I don't have ATP, make more. It's all logical steps. So what about step 10? Step 10 is a little different. On the left, it's simple. Just like with PFK, ATP binding to pyruvate kinase turns it off. AMP does not bind to it, however. Okay, so ATP binding to pyruvate kinase, just like PFK1, turns it off. How do we stimulate step 10 then? Well, on the right, with AMP is in abundance, it'll bind to PFK and activate the enzyme. Well, step 3, step 4, 5, 6, 7, 8, 9, all those are reversible from 4 on to 9. And so they just do their thing, right? I'm adding more substrate, they've pushed the flux through. But if step 10 is not keeping up with the rate of step 3, I'm not getting any products out of this, right? I'm just building up a bunch of intermediates. So step 10 needs to keep up with step 3. How does it do that? The product of step 3, the fructose 1,6 bisphosphate, Yes, it's the substrate for step 4 for aldolase, but it also goes and binds to pyruvate kinase. Now again, this is another allosteric site. It's not used as a substrate. So that's shown on the right here, this feed-forward stimulation. If fructose 1,6-bisphosphate builds up in the cell because step 10 is not keeping up with step 3, it'll go and bind to step 10's enzyme, pyruvate kinase, and make it work better. So step 10 will work faster, try to keep up with 3. And if it ever does catch up with 3, then the concentration of 1,6-bisphosphate starts to drop, and pyruvate kinase is not so stimulated anymore. So it's a way of making sure that the steps 3 and 10 remain in step with each other, right? So at the same pace. If 10 ever falls behind, it gets kicked by fructose 1,6-bisphosphate to say, hey, keep up. Right? So those should make sense on how everything is regulated. Step 1 is rather simple. It just shuts itself off when it makes enough of its product. It's kind of an isolated thing. And we let it go because I want to keep glucose in the cell. But all the other steps of glycolysis, 3 through 10, remember 2 is an isomerase, so there's nothing we can do about it. But 3 through 10 are regulated by ATP and AMP ratios. And 3 kind of tells 10 what to do, right? Keep up with me. That's the simple way of explaining those two diagrams. Right, so here's how PFK1 is actually regulated. So on the right, we have under low concentrations of ATP, meaning lots of AMP bound, it has a normal Michaelis-Menten curve, right? The normal green curve there. But if the ATP concentration gets high, right, and AMP is low now, it shifts from being the hyperbolic curve to the sigmoidal curve, the pink curve, right? So now this is telling me that ATP is binding somewhere else other than the active site. This is an allosteric inhibition, right? We won't go over into the equations for this too much. We'll do that in the lab setting instead of in the lecture. But you can tell that as the concentration of fructose 6-phosphate drops, right? So looking on the x-axis, if I start out high and go towards the origin, that the rate of the reaction will drop faster in the pink curve than it does in the green. It's to conserve resources. If I have a lot of ATP around, I don't want to turn my fructose 6-phosphate into fructose 1,6-bisphosphate because that's irreversible. I'd rather use it for something else I need. So slow the reaction down. So the pink curve going from right to left drops faster than the green curve does. That's the reason we conserve our substrate. Okay? Hexokinase, like I said, is very simple. Its product binds to it, competing with the substrate. It doesn't bind. You don't get as much product made. Very simple negative feedback inhibition. And then regulation of pyruvate kinase, that one's a little more complex. Just like with PFK1, a lot of ATP inhibits it, just like this graph you see up here. But to make it go faster, step 3 says if you're not keeping up with me, the product of step 3, fructose 1,6-bisphosphate, will stimulate pyruvate kinase in step 10. Now I know I went through that fast. You may have to look at the slides again, but make sure you can explain those logically. Why something is doing what it's doing, those are all easy logical steps. There's one that's not so logical we'll get to when we get to glycogen metabolism later, but I'll let you know before we get there. Everyone up to then will be a logical inference. All right, so here, if you have lots of ATP, slow down or shut down the process that makes ATP. If you don't have lots of ATP, ramp up the process that makes ATP.